Here we're going to look at how to simplify trigonomic expressions using some of our more basic identities. So first we have what are actually called the basic identities. So we've got sine of x, cosine, tangent, and we've got their partners, cosecant, secant, cotangent. And as you can see, we've rewritten, say, our sine in terms of the reciprocal of your cosecant. And so what we're showing here is the partner relationship and how sine and cosine, or sine and cosecant interact with each other. So we use these identities in order to manipulate our equations. Now, the interesting thing about tangent and cotangent, if you look, not only do they manipulate each other, but they also have a relationship to sine and cosine. And so you can see that here, that tangent is also the same as sine over cosine, and then cotangent is the reciprocal of that, cosine over sine. So our basic identities are showing us, again, that relationship that exists between your major and your minor trig functions. Now we have what are called even and odd identities, and if you look at these, an even and odd identity is essentially looking at what's happening with a negative x instead of positive. And so here you would evaluate and see what you get. And so when we're talking about sine, the sign of a negative starts out positive. When you evaluate with that negative, you get a negative. So this is going to spit back the exact opposite, which is going to give you the idea of odd. Whereas if we look at our cosine pairs, notice when we evaluate the negative, we still get a positive. Since we get the same thing back, this is going to emulate more along your even line. And then we have what are called cofunction identities. So a cofunction identity is essentially looking at what if I take pi over 2, which is the same as 90 degrees, and subtract away whatever that x value is. Well, what we find out is that it should give you the same as if we had just simply evaluated by the cosine. And so each of these trig functions has a cofunction partner. So you can see sine and cosine are together, tangent, cotangent are together, secant, cosecant. And of course we can reverse it and go the opposite direction. And so these are the identities that you are going to pull on when you are looking at simplifying, say, a given expression. And so we're going to look at a couple of those examples so you can see how they work. Now, a couple of the other major identities that we need to pay attention to are the ones that are called Pythagorean. So Pythagorean identities deal with the right triangle, and as you know, when working with your unit circle, we do a lot in terms of Pythagorean identities. Okay? So the biggest thing that we have to remember about those is that your x is representative of your cosine and your y is representative of your sine. And so here all we simply did is we used the idea of the unit circle, which says your radius is 1. We took our definitions for sine and cosine and we simply plugged them into our Pythagorean equation, thus giving us what's called the Pythagorean identity theorem for trigonomic functions. Now with that, we also have variations, and as you can see, they deal with the other trig functions that we have. So cotangent, tangent, cosecant, and secant. So let's see if we can put all of this together. So the problem we have is that we want to simplify the following, and we're told that we have tangent times the cosine minus cosecant. So the first thing that we want to do here is we want to treat this the same way that we would a linear problem, in that we are going to take our tangent and we are going to distribute him through your parentheses. So this is going to give you the tangent of x, cosine of x, minus the tangent of x, cosecant of x. Now once we do that, we need to apply our identities. So I'm going to look at this first half, and the only place where we can apply an identity is going to be right here with my tangent. And the reason for that is because we already know that tangent has a couple of identities that we can use. And those identities being that we know that your tangent of x can be the same as 1 over the cotangent, and we know that the tangent can be the same as sine over cosine. So how do we determine which one to use? Well, you have to look at what do you also have in your problem. And in this case, I have a cosine here. So the identity that I want to use is sine over cosine. So you rewrite it as sine of x over the cosine of x, and we're still multiplying that by the cosine. And then again, we have to look on the other side. Well, notice both of these I can rewrite. So the first thing I know is if I look at my cosecant, I know that my cosecant can be the same as 1 over sine. Well, the other thing that I have is I have my tangent here. And as we looked at from the first one, we have two choices. Well, if I'm going to rewrite my cosecant as 1 over sine, then I want to use sine over cosine for tangent. So this is going to be subtracting the sine of x over the cosine of x, and then I have 1 over the sine of x. Now if we look at both of these as a straight problem, one of the things that you'll notice is that I can cancel out my cosines, and that just simply leaves behind my sine of x. Oops. And on the other side, I can cancel out my sines, which leaves behind 1 over the cosine of x. Well, I can't say that I'm finished, because this right here is actually an identity in that we know 1 over the cosine is the same as your secant. So the last thing you have to do is one final change. So we'll rewrite it to say that we have the sine of x minus the secant of x. And this ends up being the solution that we wanted. Now notice our solution does not exactly have a number variable or value. It's left you with an expression, but that's okay because the only thing that we actually wanted to do here was simplify our expression and nothing more. Alright, let's try another one. So here I have 1 plus the tangent, and I want to square it. So the first thing that I have to remember here is that this is the same as looking at 1 plus my tangent of x times 1 plus my tangent of x. Okay? And we're going to go back to kind of the old school algebra where we are going to FOIL this together in order to multiply. So one of the things that we want to make sure we recall is we want to remember what FOIL is, first, outer, inner, last. So my first 1 times 1, so this gives me 1 plus. My outers is going to be 1 times the tangent, and my inners is going to be 1 times the tangent. So this gives me a total of 2 tangent of x. And then we're going to have last, tangent and tangent. So this is going to give me tangent squared of x. Now when we're looking at these again, just like before, we have to look at what do we actually have that we can work with. And in this case, we have what appears to be a Pythagorean identity. And the way I know that is because I have 1 and I have a squared function. So I'm going to rewrite this real quick to say 2 tangent of x plus 1 plus the tangent squared of x. And when I look, this appears to be my Pythagorean identity. And that Pythagorean identity says that 1 plus the tangent squared is going to give me secant squared. So this right here should be secant squared of x, using again that Pythagorean identity. So my answer here is going to come out to being 2 tangent of x plus the secant squared of x. And in this case, there's nothing else for us to do, so we have our solution. Alright, let's try one more. So here I have 1 over the tangent squared of theta plus 1. And if you notice, right down here, just like the problem above, this is the same as your secant squared. It is that Pythagorean identity. So this can be rewritten as 1 over your secant squared of x. And if we're looking at it, one of the things that we notice, or that we know, is that my cosine is going to be the same as 1 over my secant. So we can apply this idea to my fraction. So here I have 1 over secant squared. Well, I already know my identity says that my cosine is the same as 1 over secant. Therefore, we can rewrite this to being the cosine squared of your theta, thus giving us the most reduced form of that problem. So with these examples, the one thing that you should be able to see is that all we're doing is we're taking our basic identities or our Pythagorean identities, and we are applying the rules that they follow. Alright, let's look at another one here. So in this case, we want to factor and simplify. So one of the things that you can do when trying to factor is you can rewrite your equation in terms of x and y. And so here, I'm going to take this and I'm going to say, let, let a equal my sine of y. So when I do that, I can rewrite my equation. It now would say 4a squared minus 8a plus 4. And what I can do is I can factor this now fairly easy. The first thing I would do is pull out a 4. So this is going to pull out a 4 and leave me with a squared minus 2a plus 1. And then I can factor this down into its pieces using whatever factor method that you prefer. I know a squared will break into a, and I know my only factors of 1 are going to be 1 and 1. Since my back term is positive, my middle term is negative, they both need to be negative. And so in this case, once you factor everything down, the biggest thing you have to remember is that we started with a let statement. And when you start with a let statement, you have to finish by reinserting what you substituted. So here we would end up with 4 times the sine of y minus 1 times the sine of y minus 1, which is the same as 4 times the sine of y minus 1 squared. And that would be your most reduced form is right here, your most factored reduced form. Okay, let's try another one. So here we can do the same thing. We can say let, b equal the cosine of x. And so in this case we would have 2 b squared plus b minus 3. I don't have anything that I can pull out, so again, I'm going to fit right into my factors. So I know I have to have 2b and b. And then I have 3. And I know my only factors of 3 are 1 and 3, and they have to give me 1 as a result. And so in this case, I would have to have 3 over here and a 1 over here. Now the reason for that is because of this 2. The only way to change 3 and 1 into a 1 is if I have my 2, and so in this case I would have to have positive 3 and minus 1. So if we were to FOIL, my first is going to give me 2b squared, my outer is going to give me negative 2b, my inner gives me 3b. When I combine it I get 1, and then 3 times negative 1 gives me my negative. So I know I factored it out completely. Again, I don't want to forget that I started with a let statement. So that means at the very end I have to reverse it. So this is going to end up being 2 cosine of x plus 3 times the cosine of x minus 1. Alright, in looking at this one, I have 30 sine cubed of x cosine over 6 cosine squared of x sine. So there's a couple things that we can do with this. One, we can reshuffle or rewrite our fractions so that we have, say, matching pairs. So I might rewrite this so that I have 30, and then I have my sine cubed of x, and I have my cosine of x. And so notice I gave myself a little space, and I'm going to line up my things on the bottom underneath. So this is going to be 6. I have a sine of x and a cosine squared of x. Okay, so remember, multiplication is the same forwards or back. So when I'm looking at it, I'm going to do some cancellations. First, I know 30 and 6 can combine. It becomes a 5 on top and a 1 on bottom. I also know that my sine cubed over sine of x can change. My 3 goes away and becomes a 2. The sign on the bottom goes away. And then the same with my cosines. I can have my cosine on the top go away, and my square on the bottom becomes a 1. So if I rewrite what I have here, I have 5 sine squared of x all over the cosine of x. Now I'm not done, because I have this sine squared of x piece right here, which I can expand. And when I do that, I'm going to end up with 5 sine of x all over the cosine of x. Now if you look very carefully, notice I right here have sine over cosine, which we automatically know is my tangent. So in terms of my identity, since that's the tangent, I would rewrite this to get rid of my fraction, and I would have 5 tangent of x sine of x. And now I would be as simplified as possible. There is nothing else for me to finish, and so there I have it. Alright, let's look at a couple that are a little bit more involved. Okay, they've got a little bit more to them. So here, notice I have 2 rationals that I am multiplying together. So the first thing that I want to do is I want to factor my top and my bottom or denominator. So I want to factor those two down to their smallest pieces. So I'm going to have 5 cosine of theta over my sine squared of theta. And I'm going to multiply that to what I get on the top. So if I look, I have sine squared and I have sine cosine. So I'm going to pull a sine out. And that's going to leave me with sine of theta minus cosine of theta. And then on the bottom, I actually have a perfect square, or difference of squares. And so this is actually going to become sine of theta plus my cosine and my sine of theta minus my cosine. So when I do that, one of the things that you can see right off the bat is that sine minus is going to get rid of both top to bottom. So here I've got 5 cosine of theta over, and this can become sine of theta times my sine of theta. And I'm going to multiply this by the sine over my sine of theta plus cosine. In looking again, I have a sine on top and a sine on bottom that can cancel. And so here this is going to leave me with 5 cosine of theta all over my sine of theta times sine of theta plus cosine. Now the other place I need to look is right here. And what I need to remember is that when I had my cotangent, tangent is the same as 1, or cotangent is the same as 1 over tangent, which is the same as cosine over sine. Therefore, I can rewrite this to say 5 cotangent of theta all over sine of theta plus cosine of theta. And in this case, I now have nothing else that I can do, so I have finished my simplification. So again, it all comes down to being able to identify the different equations and identities that can be used in order to give us a smaller result or a simplified result. Alright, so at the risk of confusing you all, here's one last one, and what I want to point out about this one is that here I have a subtraction sign in the middle. And so what I have to do is I need to take that into account because this is now going to be essentially a glorified fraction. So I have to use your fraction rules to combine. And those rules say to add or subtract, you need a common denominator. And so with that, the fact that we need a common denominator, we have to do just that. We have to figure out what our denominator is and try and find out what is common between them so that we can combine your terms. So I have right here a difference of squares. And so I'm going to rewrite my fractions so that I have sine of y plus cosine of y times the sine of y minus the cosine of y. And this is my first fraction. And I'm subtracting away 2 cosine cosine of y minus the sine of y. Now, with this, notice on my first fraction I have sine then cosine. On my second fraction I have cosine then sine. So one of the things that I want to do is I am going to take this second fraction and I am going to rewrite using sine first. So here this is going to be 1 over my sine of y plus cosine of y times my sine of y minus the cosine of y. I still have a negative, and it's going to be 2 over, but in this case I'm going to have negative sine of y plus the cosine of y. So all I simply did was just rearrange my equations to write it first. Okay. Now with that, I want to go ahead and pull this negative out to make it a little bit easier to see. So my first fraction I'm still going to leave alone as the sine of y plus my cosine of y times my sine of y minus the cosine of y. This is still subtracting. I have 2 on the top, and now this is going to be negative on the outside of sine of y minus the cosine of y. Now the biggest thing you have to remember is we have minus a negative, so in our rules that essentially is positive. And so here I have to look at my least common denominator. So when I try and identify that, my least common denominator in this case is going to be my sine of y plus the cosine of y times the sine of y minus the cosine of y. So here the only thing that's missing from this second fraction is my sine plus cosine. So I am going to multiply the second fraction by that. So this is going to end up being 1 plus 2 times my sine of y plus cosine of y. And this whole thing is now over that common denominator of sine of y plus cosine of y times the sine of y minus the cosine of y. And so here, the only thing that we would really do to simplify it is we are going to take this 2 and distribute it into my parentheses. And so here we end up with 1 plus 2 sine of y plus 2 cosine of y all over that common denominator, sine of y plus cosine of y times your sine of y minus the cosine of y. And this is our combined fractions in its most simplified form. So there you have it. Everything that you would need to know to be able to get a jump start on simplifying trigonomic expressions using some of our basic identities. So if you have any questions, please feel free to let me know. If you come up with an expression and you're just having a hard time figuring out how to simplify it, feel free to send me that expression and I would love to take a look at it, give you some tips and tricks. Otherwise, I hope you had fun and enjoyed this video, and I will see you next time.